So, in the context of data flow models, we have seen briefly the Khan process network, right. It is difficult to analyze that because of that buffer issue, and now we will be discussing about another modeling language which is known as SDF or synchronous data flow. That means, whenever I say synchronous, that means there is a global clock and a global clock ticks, and at the global clock the nodes are fired. Nodes are fired at global clock, fired at clock ticks. At the same time, we use, let me write it in this way, asynchronous message passing for communication. So, it may appear to be a little confusing that we are calling it synchronous data flow, but this is asynchronous. The message passing is asynchronous, right, but the so that means what we mean by asynchronous message passing is that the tasks do not have to wait until the output is accepted. Okay. This means it gets the data, it produces some data, it sends it, right. At every clock it goes on sending it. Now, it is not necessary that it will wait for that to be accepted. So, now SDF will give some examples of SDF to you. It is. So, let us look at an SDF diagram. Suppose we have got a task A, which is a multiplication, and a task B, a task B, which is an addition. All right. And A is getting input from two data sources, and B is getting the output of A and something else. Now, these nodes are known as actors. These nodes are called actors. Now, the actors are ready when the necessary number of input tokens are available and enough buffer space is available at the output. Okay. Actors are ready if and only if required number of input tokens are available and enough buffer space is available at output. Now, we can have two types of, now is it clear? Say for example, I have got required number, say I can put in weights to these edges. What does it mean? It means that this input, only one token is required at this input. At this input also one token is required. So, if I have a token here and if I have a token here, then this is ready to fire. And suppose there is no token here. I am saying here also 1, that means one token will be produced after multiplication and no token is there. So, therefore, buffer space is available. If I fire it, it will come. Now, suppose some token is available here. I am showing another instance, some token is available here and no token is available here. Therefore, this is not firing because the and this is also 1. All right. Now, this one, can it fire? Suppose the tokens are here 1 1, no, it cannot fire because there is not enough buffer space, this is not consumed. Okay. All right. Now, there can be homogeneous SDF and non-homogeneous SDF. What is meant by homogeneous SDF?
So, we have asynchronous message passing. So, won't data be lost here? Because if they arrive and there is no buffer space available, so they will be lost.
That is what I mean, we will have to manage that, we will show that. I mean that if the buffer space is not available, then it will not fire at all. Homogeneous means, homogeneous SDF means that the same number of tokens, the number of tokens accepted at different node points are all the same. Say for example, everything is 1, the same number of tokens per firing, and non-homogeneous, this implies the same number of tokens generated per firing. Okay. So, if this fires, there will be one token generated, but that is not the general case. We can also have non-homogeneous, and in fact, we will be looking at the non-homogeneous ones more. Okay. So, for same actor, I am just showing an example. Say for example, this is a typical one, all right, and here I have got the edges 1, 1, say 3. That means, if this one fires, this is a multiplier, if this one fires, it will generate 3 tokens, whereas this is 1 and this one consumes 2 tokens and it produces 1 token. This is a non-homogeneous scenario, right.
What is the buffer space? How do we need?
Now, I have not yet given the buffer space. Right now, there is, I have not put in any buffer. Let me proceed. Okay. I have not put in any buffer right now. So, I am just saying that this is a non-homogeneous. So, what happens if I now put the buffer space? Now, suppose I put in tokens here. There are 4 tokens here. There are 4 tokens here and 4 tokens here, and there are 4 tokens here. What it means is, this has got the requisite number of tokens. Why requisite number of tokens? 1 is required. So, as this one fires, this one is consumed, this one is consumed, and here I will produce 3 tokens. Now, this one is ready. Why? Because this needs 2. So, this one will be taken up, this one will be taken up, this one will be taken up, and 1 token maybe will be produced here, right. That is the flow. Now, 2 are being taken. Now, what will happen? This one, can this one fire? Can A fire again? Why can A fire again? This one is available, this one is available, but is there enough buffer space? At least 3 can come here. So, there is buffer space, at least 2 can come in, right, but not at least 2 can come in. As soon as it fires, 3 will come in here, 3 will come in, because this is producing 3, all right. So, now let us put in a buffer at this point. So, the same thing. So, I put in a buffer here. So, this is 3 tokens, this is 1, this is 1, this is 1, this is 2. Now you understand that here I am putting 2 and here it is 1. So, here again I put in 4. Now, all of you can yourself work out and animate it to see what will happen. 4 here, 4 here, 4 here. Now, what will happen in the first shot? In the first shot, what will happen? This one is ready. So, here this buffer is completely empty. Therefore, this one will be consumed. Here I had 4. So, 1 will be consumed, this one will be consumed, and I will have 3 tokens here coming here. And since I have 3 tokens coming here, this one will fire, okay. This will consume 1 and it will consume 2 from here, and 1 token will be produced here, right. Next, this one will fire again, A will fire again, B is ready and B can fire. So, B has fired already. Now, here B cannot fire right now, although A has got, but here I do not have 2. Therefore, again this fires, this one fires, this one also fires, and I put in 3 here. So, let us put in again 3 is there, this one is not there, all right, this is not there. So, 3 are there. So, again this fires, this goes off, and 2 will be consumed from this. So, this goes, and 1 will again be produced here. In that way it goes on, all right. Ultimately, in this way as it goes on, ultimately what will happen? Ultimately, there will be a situation when the buffer is empty, everything is being consumed. Now, you see the buffer is not being full, because if there is no buffer space, if there be 4, suppose all the 4 have come here, then I am not firing this any longer, right. So, I am not being able to fire this any longer, because the necessary condition is that the space must be available in the buffer space. So, if you animate this repeatedly, then you will find ultimately, say for example, at a particular point we will have, you see this situation will come, that we have got 1 token, 3 tokens left here, 1 token here, 1 token here, and 4 tokens here. At that point, so this is 3, this is 1, this is 1, this is 2, this is 1, this is 1. At that point, who is ready to fire? A is not ready to fire, B is ready to fire, right. So, B, as B fires, this one will go. So, this is ready to fire, this one will go, and 2 go out. So, as B fires. Now, at that point, can A fire? A cannot fire, because there is no space. Can B fire? B can fire. So, B will fire here, these two will be consumed, and this. So, that is a complete period that the buffer has become empty. That is how typically SDF works. And so, as one period is complete, we will again start. Now, the question is, there is an interesting point here, that how do you model the buffer? Are we going to draw the buffer? So, if you just think a little bit, it will be immediately clear to you that we can very nicely model the buffer in this way. Say my buffer space was 4. So, I have a token here, I have a token here, and I have a token here, and so I put in the weights 1, 1, 1, 3. Now, if I put a reverse edge here and put in 4 tokens at this point, what happens? Because my buffer space was 4, so at any point of time, now what does this mean? This means whenever this fires, a token, this will fire when this 1 will be consumed and 1 will be consumed from here. What are the input data points? 1, 2, 3 now. This signifies that as this one fires, one of the buffer space is consumed. These tokens are actually showing how many buffer slots are available, empty. So, this will be there, A fires. Okay. As B fire, it will produce a token here, it will also produce a token here. That means, as B fires, it is creating an empty space. This by default is 1, this by default is 1, this is also 1. Will this be 1? This will be 3. This is 3, that is why I am not showing it. This is 3. So, when this one is firing, actually I am consuming 3 tokens from here. 1, 1, I am producing 3 tokens, that means 3 buffer spaces are gone, right. And then I have got 3 here, I have got 1 here, and B can produce, and as B produces, B puts in, B consumes 2, right, B was consuming 2. So, then 2 it returns again here, all right. In that way, we can model the buffer. Now, one of the conditions, now let us look at this diagram. Say I have got 2 processes, one is A and B I was showing. So, I am showing fire A, I model it as a producer consumer problem, and B is fire B, B is consuming, right. So, consume something M is producing N, it is consuming M, all right. You are aware of the producer consumer problem typically, and here is a channel, and channel is nothing but a FIFO buffer. Now, it is synchronous, but again these are the 2 processes. Now, they can be multi-rate, models. That means, the number of tokens being produced by this and the number of tokens consumed by this, since it is asynchronous, they may be different, right. Therefore, in order to have a balance in this data flow, what is the condition that we need to meet? The condition is, if I have say f a, if by f a I denote the number of tokens produced, n is the number of tokens produced, all right, here, and f a is the number of firings per iteration, then I am producing so many, right. This must be equal to f b m. If this condition is satisfied, then there will be a balance. Okay. So, this is a very important condition for SDF, and the advantage is it is decidable. I can find out what is the buffer memory requirement by looking at the multi-date. I can find it out much more easily, which was not that explicit in Kant's model. Okay.
Less than equal to in this case.
Which one?
The equation.
Yeah, this is a balance, absolute balance. So, as long as it is less than equal to, it will run fine. Okay. It is a perfect balance equation. So, last I will conclude SDF with an example of the possibility of parallel scheduling in SDF models. Say for example, I have got a task A, all right. I have got another task B, I am denoting in different shapes. Another task is C, all right. And the data flow is like this. C depends on A and B, and C produces something to maybe another one, which is D, and D again feeds to B. All right. Now, I want to schedule it. You see, once I get the data flow, I can schedule it in this way, that I can first schedule A. So, maybe I draw the schedule part here, here is the time. So, I can schedule A, then I can schedule B, then I can schedule C, and obviously D can be scheduled after C. So, maybe D. That is a sequential schedule. This is a absolutely sequential schedule. But my data flow graph tells me about the dependence, and therefore, I could have arrived at a parallel schedule, where I could have scheduled A, and while A is being done, I could have scheduled B, and A or B are both finished by this time. So, I next schedule C, and then I have to schedule D. Thereby, I can save the total execution time, and that is very much clear from this data flow diagram.
So for B, input from D is required.
No, initially the first time, initially D is, I am starting from this point, right. So, I am starting with A and B. Some data is already there, because D has not yet executed, otherwise it will not start. So, A and B starts, and after D next round, D can only start, B can only start after D has completed. Okay. Yeah, then the condition is satisfied. So, SDF is little easier to analyze, its analyzability is better, its implementation efficiency is better, but its expression power is very restricted, and we always have, we will see that we have to make a balance between these two. Now, before concluding this part, I will just introduce you to the notion of Petri nets, and later on, if there is scope, I will discuss about the application of Petri nets, but here I am utilizing about 5-10 minutes just to tell you about what this Petri net is, because you will find it, you can find it handy in many other things. A Petri net, I am very informally telling you Petri net. Petri net is a net consisting of places and transitions. All right. There are different forms of Petri nets, but let us start with this, that say for example, these are two places P1 and P2. So, P1 and P2 and maybe P3 also will come, are belonging to the set P, all right, and there are some transitions. Just like a graph, I have got some transitions, say T1, T2 belonging to T. T1 is a transition that fires when there are tokens available at both its inputs P1 and P2, and one variety of Petri net says that this transition T2 will fire or will be enabled if the output place, these are the input places of T1, this is the output place of T1, if the output place is empty. But there are other varieties of Petri net which associates some capacity with each of these places. That means, how many tokens can be there. This is very similar to our buffer thing that we are thinking of. So, simply speaking, right now let us assume that by default its capacity is 1. Therefore, this transition can fire only when both these inputs are, both these input places have token and this one does not have a token. So, this will fire. As it fires, this will come to that these tokens are removed and a token will come here. So, this will be transformed to, as soon as this firing is done, the scenario will be this. And maybe in this transition, we had something like another transition T2, which is also in T, okay, and there is a output place here. So, P1, P2, P3, this was P3 and this is P4. Now, as this fired, then what will happen? This, suppose this one already had a token here, but this could not proceed. Now, as this fired, there was a token already here. So, this transition will also fire, and as this transition will fire, we will have these two tokens removed and will come here, and this is completely asynchronous. There is no need of a clock. As soon as the tokens are available, these transitions may fire. Now, there are different varieties of Petri net. which says that along with these transitions I can put in some conditions that even if these are available. Okay. Now, say for example, there is a situation where there is a single railway track and trains can come, any one train can come through this track obviously. Either a train can come from this or a train can come from this. And you are designing a signaling system, so that there is no accident or something like that. Now, this how now you have designed something, a system. Now, that system or the requirement can be nicely specified using Petri net. For example, let us try to do it. Let us try to do it and see if we can. Have you got this problem? All of you have got this problem that. So, I can have one place saying track available. Suppose this is a place which says track available. Okay. And there is a place and there is a transition. A train has come and this transition T1 means the train will move to the right. All right. This is the meaning of this transition. Now, I will allow the train to move to this direction only if the track is available. So, if I model it like this, then the train can move if both the conditions are true, and as soon as the train moves across the signal, it comes here, then this token is consumed, the track is no longer available. Okay. So, now if at the same time another train is coming on this side and trying to come on this side, it is also connected here, and therefore, you can see that cannot proceed, because once one train is moving in this direction, it cannot proceed. Now, when it goes out of the junction, then now this has been consumed. Now, as it moves out of the junction, that is moves out, then it can return the token here, and then this one can proceed. So, in this way I can represent this scenario. Now, connect this scenario to your embedded system scenario, that you can have resources, or in operating system I was mentioning about operating systems time and again. Now, in operating systems also we are using resources. So, will there be a deadlock situation, or is it a live situation that ultimately the trains will pass? How is my design? If does my design allow that the track will be ultimately available for all the trains to pass? Is it the case that all the processes will get the necessary resources so that it can go through this, so that they can run to completion? That is a liveness property. So, all these can be analyzed very nicely using Petri net representation. Okay. So, that is, and once we do this, there are, I am not discussing that in detail in this here, that this can, this has got different varieties with the number of tokens that each place can have and all those. Now, it can be translated to a matrix representation, where we have got the places and the transitions, and through that matrix representation we can have a matrix representation, and using linear algebra we can do a lot of analysis on this, and that is why this comes in very handy. Okay. We can carry out a number of analysis and prove many properties of a system.
How is it different from SDF?
This is asynchronous, absolutely asynchronous. SDF is synchronous, and in SDF we are, it is similar, but this one Petri net is asynchronous completely, and these transitions and all those, there is no explicit condition of a buffer, it is in the capacity and all those.